week 3 of the problem solving session for the course Introduction to Fluid Mechanics. And just anyone please let me know if I'm audible, like the thumbs up or a yes in the chat box would be good. Okay, thanks Agas, thanks Shanawaz, thank you. Okay then, so this week's discussion would be primarily focused upon two important concepts. First is surface tension, and second is the principle of manometry, and we'll see how we use or implement manometers to calculate the pressure at different ducts or pipes. Okay, we'll look into some examples, and then as per our regular agenda, I will go through the concepts taught by Professor Chakraborty in the lectures. Briefly, I will go through them, and of course, this week's topics are not that elaborate. Not that it's not that not content of this week's session is not that much. So we will just be focusing on two topics discussed by Professor Chakraborty in the lectures, and then we will directly go to solving some questions regarding these two concepts. Okay. So to begin with, so as I already mentioned, I will not dive deep into each and everything. Maybe sometimes I will just take the key formula that was derived by Professor Chakraborty in the lectures just to save time, and that's the instruction that we get, that we should just discuss briefly about the concepts and focus more on the problem solving part. Okay, so with that idea in mind, let's discuss about surface tension. So the concept of surface tension arises from the understanding of cohesive and adhesive forces. So these are two types of forces that might have been described by Professor Chakraborty in the lectures. So cohesive forces are the types of forces that are encountered by a fluid molecule with the other fluid molecule that surrounds that particular fluid molecule. So the forces between the fluid molecules contained in a container, say, are known as the cohesive forces. And the forces of attraction between the fluid molecule and the surface of the container in which it is stored are known as the cohesive forces. Okay, so these are two types of forces. Like, basically, if you want to put it in a more scientific manner, then it would be like if the types of forces between the molecules of same kind are known as cohesive forces, and if there is a heterogeneous scenario where two different types of fluids are in contact, or different types of states of matter such as liquid or solid are in contact, then the forces of attraction between the liquid and a solid, or the liquid and other different type of liquid, are known as the adhesive forces. Okay, so with that idea in mind, so it is with the help of that principle that the concept of surface tension comes into picture. So here the concept of surface tension is valid in the case of an interface. So for example, if you consider a liquid contained within a container, and there's an interface, I'll just label it, there's an interface of a liquid and vapor and on the surface. So we see that since there's a density difference between the gas and liquid phase, so there will be distinction between the forces of attraction for the molecules in this region which are attached to the liquid phase, and the molecules that are attached in the vapor phase. So there will be a distinction of forces because of the density variation, and because of this there is a resultant force on these molecules which are on the surface of the interface, which inherently would like to break this molecule apart, but still we find that the molecules on the surface tend to retain their shape. Okay, tend to retain and hold their presence at the interface. Okay, so it is, and that's why these molecules have some additional energy within them, by the virtue of which they are able to sustain their position at the interface by overcoming these net attraction forces, and this energy is known as the surface energy. Okay, because of this discrepancy in the magnitude of the forces in the liquid phase and the vapor phase, there is a tendency of this liquid bubble to break apart, but still they tend to hold their shape, and it is by the virtue of the surface energy by which they are able to hold their shape. Okay, and this force, that is additional force that is applied by the liquid to hold its shape per unit length, is known as the surface tension or the surface tension coefficient. Okay, so again there is a brief derivation of the Young's equation, so I will just briefly go through it. Of course it is not that quite relevant to the problems that we will be discussing in this week's session, but still I will just like to go through it once because it was discovered by Prof Chakraborty. So here is just consider a liquid bubble on a surface, on a solid surface, and we just try to do a force balance along the x direction. Okay, so this sigma ls, sigma sv, sigma lv, these are different kinds of surface tension coefficients at different interfaces. So sigma lv denotes the surface tension forces in the liquid and vapor interface, sigma ls denotes the surface tension force along the liquid and solid interface, and sigma sv denotes the surface tension forces or coefficient, surface tension coefficient in the solid and vapor interface. Okay, so this dissociating these forces, so if we do a force balance along the x direction, we would get sigma ls plus sigma lv cos theta. So the component of the sigma lv force along the x direction would be sigma lv cos theta, would be equal to sigma sv. Okay, and then this angle cos theta is again given by sigma sb by sigma ls divided by sigma lv, and this is known as the Young's equation. Okay, so there was an elaborate discussion by Prof Chakraborty of finding the expression for excess pressure. Okay, so as an exercise, I would encourage all of you to go back to the lecture and just try to derive, if you have not derived it yet, try to derive this expression for excess pressure. So it takes a curved surface and tries to find the expression for the excess pressure in that curved surface, and he found out that the formula for excess pressure on those curved surfaces are given by delta P, that is the excess pressure, is equal to sigma, this is the surface tension coefficient of that particular liquid, times 1 by r1 plus 1 by r2. Okay, these are different radii along the different axes. Okay, so this is actually the general formula. Okay, and of course there can be, if you want to generalize it even further, again it can be done, but now we would like to look into the special cases. Okay, so there are two special cases here that we have considered. That is, first is a spherical droplet and there's a spherical bubble. Okay, so in this formula, if we substitute the value of, for a spherical surface, then the value of r would be same in both the cases because the curved surface will have the same radii. Then r1 is equal to r2 would be equal to r, that is the radius of this spherical droplet. Then the formula of excess pressure turns out to be delta P is equal to sigma by r. Okay, where sigma is a surface tension coefficient. But in the case of a spherical bubble, for example a soap bubble, like, it will have two surfaces. First is the surface within a, basically it is a hollow bubble, that's why it will have two surfaces. First is the inner surface and then is the outer surface, and that's why this excess pressure formula would be multiplied by 2 because now there are two interfaces acting to hold the shape of the bubble. Okay, so we will have the excess pressure formula as delta P is equal to 2 into 2 sigma by r, just implementing this formula again. Then we get delta P or excess pressure as 4 sigma by r. Okay, and as shown in this diagram, the excess pressure, the concept of excess pressure comes from the fact that there has to be an excess pressure within the bubble that is greater than the outer pressure or the atmospheric pressure or the surrounding pressure that would keep the shape of this bubble intact. Okay, so there will be a pressure acting in this direction that should be greater than the surrounding pressure so that this bubble is able to hold its shape. Okay, and that's why it's termed as the excess pressure. Now we look into another important concept, that is the concept of capillary rise. Okay, so again this is we can derive it by understanding the concept of surface tension, where to find the expression for capillary rise we basically do a force balance between the surface tension forces and the forces due to gravity or the weight of this liquid column. Okay, So for example, if you consider a case where you place a thin capillary tube, okay, so a thin capillary tube, I must say, is basically a tube of very small diameter. You might have seen this in the case of in the chemistry lab where, or biology lab, where you find very thin glass tubes, where you, if you place those glass tube in a particular liquid surface, you will see that the liquid level within the glass tube will rise, and this rise basically because of the surface tension forces or the adhesive forces between the liquid and the surface of this glass tube. Okay. And as Professor Chakraborty might have mentioned, this phenomenon has a crucial role in the rise of liquid levels or water levels from the roots of the trees. Okay. So yeah, the rise of water in the root of the trees, or which is known as the ascent of sap. Again, this rise of water from the roots to the upper parts of the trees, of tall trees, are primarily driven by transpiration from the leaves of the plants, but still there is a certain role of this capillary rise in the rise of liquid levels in the roots of the trees. Okay. So keeping that idea in mind, so let us consider a case where we place a glass tube. It's again a schematic diagram. So actually the diameter of this, if we consider this container, then diameter of this pipe should be of something like this. Like it should be very small, but we are using a schematic diagram to represent the different kind of forces that we are going to balance. Okay. So let the H be the rise of this liquid column in this particular capillary tube, and let R be the radius of this capillary tube. Okay. Then say this is the kind of the interface that is being formed in the case of this particular liquid, which is say water in this case. So if we now dissociate the forces that are acting on the interface, we can find that there is a pressure due to the atmosphere from this in this direction. Then there is a pressure because of the liquid column in this direction, and there are these surface tension forces that acts along the interface of this surface. Interface in this interface. Okay, in this interface of this liquid and gas, air in this case. Then we find that this kind of interface, or which is also known as meniscus, is formed when the pressure due to the gas is higher than the pressure due to liquid. Of course, it's intuitively understandable. I'm extremely sorry. Just wait for 1 second. I have to take this call. Just 1 minute, okay? Hello. Okay, I'm extremely sorry. I had to take this call. Sorry for the disturbance from my end. Okay, sorry for that. So as I was mentioning, yeah, this kind of interface is formed when the pressure due to the gaseous phase, or in this case denoted as Pg, is greater than PL, and this is intuitively understood. Like if you look back, like this kind of interface is formed when the pressure within the liquid phase is higher. That's why this kind of curvature is formed, right? So it will, in this case, it will be PL is greater than PV. But in this case, for this particular liquid, which is water in this case, this is the form of meniscus that is formed. So the pressure in the gaseous phase is higher than the pressure in the liquid phase. Okay. So once we dissociate these forces acting on a particular direction, and since the weight of this liquid column will always act along the direction of gravity, then we do our force balance along this direction. Okay, along the vertical direction. So once we do that, okay, I'm just skipping the let us just take it. It's fine. Okay, I'll just take it. So if this is the surface of if this is the shape of our interface, that is a meniscus here, then let R be the radius of curvature of this meniscus, okay, this small r, okay. But this small r is a parameter that we do not have in our control, okay. We do not actually know what would be the, or it's very difficult to calculate or evaluate the value of this radius of curvature of this meniscus, okay. So the parameter that we have in our control is the radius of this capillary tube, okay, that is the capital R. So ideally we would like to have a formula in terms of the parameter that we are able to control, okay. In this case, the parameter that can be controlled is the radius of this capillary tube, okay. We can use a thicker or thinner capillary tube depending on the level of liquid rise that we want to have, okay. So keeping that idea in mind, we would like to have this expression for this capillary rise h in terms of parameter that we are able to control, this in capital R. So but in the formula of excess pressure, that is delta P, we know that we have R1 and R2 as the radius of curvature of the interface, but not the tube within which this interface is formed, okay. So with keeping that idea in mind, we need to substitute this R1 and R2 as small r and not capital R, okay. So R1 and R2 will be small r, that is the radius of curvature of this meniscus. So with that idea in mind, we will have delta P as 2 sigma by R, okay. And R, if we look into this diagram, will turn out to be R would be capital R by cos theta, okay. Or basically R cos theta would be capital R, then small r would be R by cos theta, okay. We just substitute this in our expression. So we have delta P as 2 sigma cos theta by R. Just substitute small r by capital R by cos theta, you will get delta P as 2 sigma cos theta by R, which would be equal to rho gh, or the pressure or the pressure due to this liquid column, okay. Then if we equate these two values, we'll find that the pressure, the capillary rise small h is given by 2 sigma cos theta by rho gr, okay. And in this expression, you can see that there are terms such as the surface tension coefficient sigma, the density of the fluid, the gravitational acceleration g, and the radius of the capillary tube, okay. So from this we can say that this capillary rise h depends on the contact angle theta, because it will determine, of course it's here itself, but it will also determine the shape, the type of meniscus that is formed, okay. Then the radius r, that is the radius of this capillary tube, then type of liquid which is being considered by the density of the fluid, then miscibility between the fluids, that is the solid and these two interfaces, that is, it is air in this case, but in certain cases there may be scenario where there can be different type of fluid here, and this interaction between this fluid screen is not visible, okay. So okay, I'm sorry, Akash is saying that screen is not visible. Is this the same problem to others as well? Like, are others also not able to see the screen? Oh, now okay, fine, thank you, Akash. I was also concerned, but it's fine, okay then. So yeah, so as I was mentioning, there might be a scenario where instead of air, which is the fluid in this region, there might be different kind of fluid, and the interaction between that fluid and the fluid in which we are finding the capillary rise can affect the shape of this meniscus, okay. And thus it will again result in a different value of h, or again we have to modify the formula accordingly, okay. And of course the surface roughness, like if the surface roughness is high, then again it affects the capillary rise, okay. And there is again a different scenario, there's again a different case where the static contact angle is an obtuse angle, so it forms an obtuse angle with respect to the let me go back with this vertical, okay. There is basically a meniscus is formed in this manner, so the contact angle would be something like this. So in that case, again the expression changes accordingly, and those kind of meniscus are formed in the case where the adhesive forces between the liquids are higher than the adhesive forces between the liquid and the capillary tube surface is lower than the cohesive forces between the type of liquid used. So And these kind of meniscus are usually formed in the case of mercury. Like if you trying to find the capillary rise in the case of mercury, which would basically be a capillary tip, the liquid level in the capillary tube will fall down instead of rising up. So in that cases, the angle of static contact angle is an obtuse angle. So the formula of this capillary rise or capillary fall changes accordingly. So we can write delta P as 2 sigma cos theta 2 sigma cos 180 minus theta divided by rho g r. So this is the modified case in the case of an where the contact angle is greater than 90 degree. Okay, and this delta P or the excess pressure is given by H into rho Hg minus rho W. We have just used two general cases. So so rho Hg would be the density of the mercury. Okay, let me, I think, just 1 second. Okay. So so I hope it's clear till now, the capillary rise, the capillary surfaces and the capillary rise part. I hope it's clear till now. Okay. Okay then. I think these two topics that we are discussing today are more on the problem solving part. So configuration. Okay, let me just check what you are mentioning. Configuration. So I'm just looking at Ketan's doubt. Then I will just see whether I can help him. Okay. So if we express the surface energy and set out its partial derivative with respect to say r and theta to 0, then we will get corresponding expression for equilibrium. But that these expressions do not automatically ensure that the second derivative is positive. That means it ensures zero gradient, but it does not ensure that it's minimum. Please explain what does it mean. Okay, so okay, let me get this. See, this is just a concept of like what you're trying to mention is the concept of minima and maxima. So, like if say with respect to a particular point, if you're trying to find whether a function has a minimum or maximum at that point, so if the second derivative of that function in that particular point is negative, then it would mean that there is a maxima at that point, and again vice versa. If it's positive, then there's a maxima. If it's positive, then it's a minimum at that point. Okay, so that's what I am trying to understand by it. Okay. Get the corresponding expression for equilibrium. Okay, but these expressions automatically ensure that the second derivative is positive. That means ensures zero gradient. Ensure that so I think I do not know whether this question is from a textbook or is from the assignment, but I think whatever the question is, I would need to see the expression for that, like whatever expression they are mentioning. But if that's the case, then it seems like you have to find the second derivative of that particular expression for say the surface energy. It was in lecture. Okay, so okay, like I think it is something that Professor Chakraborty, I also saw the lecture actually, but I might have missed this part, but correct me if I'm wrong. So it seems like it is something like that Professor Chakraborty might have just discussed rather than deriving it entirely. Like, so it's something that he wants to ask the students to do. So it might mean that he's trying to discuss something like if you may get interesting instabilities in droplets and bubbles. Condition therefore these are necessary conditions for equilibrium, but not sufficient. So even in this considered satisfied, you may get still interesting instabilities in droplets and bubbles. Okay. Okay, just okay then. Let me just put it in this way. So for the first part, the first discussion that you have done is first is like, it's something like if you want to find the expression for surface energy, that would basically be sigma into A, if I'm not wrong, the surface energy. Then you will need to try to find a scenario where the surface energy, which kind of shape or scenario would result in the minimum surface energy. So that we have to find out using the double derivative of that particular expression. That's one thing. You will get a particular value of theta or whichever r that you are given, that will give you the value of the lowest level of surface energy. That's one thing. That we can do. Second is regarding instabilities. So this part I am not sure from my end. Okay, I'm sorry. Instabilities in droplets and bubbles. So that part I think I have to look into it. Okay, and moreover, for the within the scope of this course, I think this is well beyond the scope of the discussion that we are having. These are advanced discussion, and Professor Chakraborty might have himself mentioned it. Like, these are things that can be done beyond the scope of basic fluid mechanics. Okay, so with that idea in mind, like, I'm extremely sorry, I am not aware of this kind of instability between droplets and bubbles. So I will have to look into it. Okay, Ketan, if you don't mind. But thanks for putting it out in the class. Okay, thanks. I will look into it and discuss and clarify it hopefully in the next class. I will look into that expression, try to drive it myself, and hopefully discuss in the next class. Okay, thank you, Ketan. And sorry if I'm not able to clear, but I will try to clear it in the next class. Okay then. So with that, with this discussion, let us proceed to the concept of fluid statics. So as I was discussing, this fluid mechanics is a very vast subject actually. So it can be distributed in different portions, and fluid statics can be considered to be one of the earlier stages of this course. Okay, so after that we'll look into the fluid kinematics part, where okay, as the name suggests, fluid statics. So in this case, we will be dealing with the scenarios where the fluid is at static state, or it can be considered as a rigid body. Okay, so this condition is very important. Again, this is an interesting topic of discussion, and there is a very elaborate discussion taken by Professor Chakraborty to define how we are able to consider fluid particles in motion as rigid body motion, and then apply these equations of fluid statics. Okay, so I think this is an interesting exercise for you guys as well. I would suggest that you can go back to the lectures by Professor Chakraborty, where he just starts the fluid statics part. Okay, so he has done a very elaborate discussion about why we are able to consider the fluid body under rigid motion and apply the equation of fluid statics in those kind of scenarios. Okay, that's why this fluid under rigid body motion is also taken as a part in the fluid statics. Okay, so I will like that if somebody of you are interested enough to understand why we can do that, because it's a counterintuitive scenario. Like, you're saying is motion, and then you're clubbing it inside fluid statics. Okay, so there is a scenario where he discusses, like, since there's no deformation in the fluid element because of the shear forces, we can apply this fluid statics equation on fluid particles moving in rigid body motion. Okay, so I would encourage that if you go back to that particular portion of the lecture, understand it properly, and if you have any doubt, you can put it forward in the next class, because next class also we will be discussing the fluid statics part. Okay, so if there's any doubt regarding the rigid body motion part, because it's an extensive part of discussion for this course, so we can discuss in the next class. Okay, I would suggest all of you that, and that's why I left that discussion part in this derivation. I'm just taking that particular fluid element, doing a force balance, and then trying to find out equation of motion in the fluid statics part. So as I was mentioning, there's fluid statics, then we will discuss about fluid kinematics, where we will see fluid bodies in motion, then the shear forces will come into picture, and then finally we'll look into fluid dynamics part, I guess in the last part of this course, like what are the forces that causes this motion of fluid. Okay, what are the forces that are behind the motion of fluid. Okay, what are driving factors that causes these fluids to flow? Okay, we'll look into that. But right now we are just interested in the fluid statics department, like considering the cases where the fluid is under rest or under rigid body motion. Okay, so with that idea in mind, let us look into this derivation. It is basically a force balance for a particular fluid element, which is where the shape of the fluid element is taken as to be in a cubical form, just or a cuboidal form, just to simplify the expressions. Okay, and moreover, this shape it can be considered to be quite generic in the case of a Cartesian coordinate system. If you are finding it these expressions in a cylindrical system, then you have to modify your coordinates in cylindrical coordinates, or a spherical fluid element, then you have to modify your coordinates in spherical coordinates. That's just the thing, but it's quite, for basic understanding, it's easy to discuss in Cartesian coordinates part. So we are taking the fluid element to be in this form. Okay, and the width of this fluid element is again taken to unity, just to simplify our calculations. Okay, so let us consider this fluid element. So let this edge, let me just name it. I think it would be okay. I think it would be just wise to name these edges B, C, D. Okay, let us consider these edges named as A, B, C, D. So A is at, say, the say if A is at X, then B, say if the length of this section AB is delta X, then B would be at a distance of X plus delta X. Okay, then the pressure at this surface AD, oh, I'm sorry, this surface AD, okay, would be P into delta Y into 1. Okay, so Y delta Y into 1 would be the area of this surface, right, within the depth of this paper. So then the area would be delta Y into 1. So pressure, the force would be P into area, this delta Y into 1. Similarly, in the other phase, the pressure would be in this direction, as I already mentioned in the first week's discussion, that pressure always acts in the inside against the direction of the area normal vector. Okay, so it acts in this direction. It applies a compressive force. So in this case, it would be, the pressure would be given by P plus dou P. Okay, again the naming part. So Professor Chakraborty also might have mentioned dou P as the partial derivative. So I also like to use it as call it as dou P. Some professors or some tutors might use it as delta P or del P. Okay, but for my convenience, I like to mention the partial derivative as dou. Okay, this is dou P by dou X. So I would mean that it is the partial derivative of pressure with respect to X. Okay, just it's a choice of words that I use to mention this partial derivative. Okay, I hope that does not create any confusion, because I like to call this is this triangle shape as delta. Okay, that's why I'm just to avoid this confusion, I am mentioning it like that. Okay, so pressure at this surface would be P plus dou P by dou X into delta X into the area, that is delta Y into 1. Again, it's a symmetric shape, so the area would be same in this edge as well. So the interesting part was how we found out that the pressure at this surface would be P plus dou P by dou X into delta X. Okay, so it's simply the Taylor series expansion of pressure at a point X plus delta X. Okay, X plus delta X, then pressure at X plus delta X would be P plus dou P by dou X into delta X, that is this distance, plus dou square P by dou X square into delta X square by 2 factorial. Okay, so this is just the Taylor series expansion. So again, for more details like how we have derived it, so it's just a mathematical concept in series expansions, about the Taylor series expansion. So I would suggest that you can go back to the mathematics textbooks to find out the Taylor series expansion. Like for example, a function f into x plus h, what would be Taylor series expansion? Okay, so it would just be fx plus h into f dash x plus h square by 2 factorial f double dash x. Okay, it's just, and then some other higher order terms. Okay, so it's just found out like that. Similarly, if you just substitute the value of h as delta x here, and f as p, you will get the same expression. Okay. So okay, just to generalize it even further, like if I'm doing it along the x direction, sorry, so I can, instead of writing as f dash x, I should write actually dou f by dou x and dou square f by dou x square. Okay, along the particular coordinate direction, because f can be function of x and y as well. Okay, so with that idea in mind, and here also, since pressure can be a function of x, y, z, so that's why you're using partial derivative. And this bx is the body force per unit mass along the x direction. Okay, so if we do a force balance along the x direction, we'll get summation of fx as max. Again, the confusion behind this fax would come when we understand why fluid statics can be, fluid under rigid body motion can be considered within the fluid statics department. So you can look into it, and we'll discuss it in the next class. Okay, if you have any confusion, then we do the force balance. So P into delta y, there is a pressure force along this direction, minus P plus dou P by dou x in delta x. So I'm just taking the first two terms, okay, and the higher order terms, again it will be negative if delta x very, very small. So if we consider delta x very, very small, then delta x squared is even further, it's further small. Okay, if we consider delta x is 0.01, then delta x square would be 0.0001, right? It is again very, very small, so we can disregard the contribution from these higher order terms. So with that idea in mind, we can write the force along the x direction in the negative x direction would be minus P plus dou P by dou x and delta x into delta y. Okay, delta y into 1, we can just disregard the 1 and write it delta y, plus rho into delta x and delta y. Again, volume would be delta x into delta y into 1, that is the depth along on this, inside this direction of this paper. Then it would be rho into delta x and delta y into 1, the volume, into the body force per unit mass. Okay, because density times volume would be mass, so this is body force per unit mass, so it will, the unit of this expression would be newtons. Okay, force. Finally, it is again mass into acceleration, this is rho into delta x and delta y into 1 into ax, that is acceleration along the x direction. Now again, if you simplify this expression, you will get that minus dou P by dou x plus rho bx is equal to ax. This is the equation of motion for fluid statics along the x direction in the Cartesian coordinate system. Similarly, you will get expression as minus dou P by dou y plus rho by is equal to rho ax, and minus dou P by dou z plus rho bz is equal to rho ax. This would be the three equation of motion for fluid statics in the Cartesian coordinate system. Okay, so now if we consider a case where we are trying to find the pressure at point P, and we can again apply this expression, this equation of motion, because the fluid is at static state, and Professor Chakraborty might have emphasized the use of this expression, of this symbol, that is a inverse delta and these two lines where the lower line is smaller than the upper line. So this symbol is used to denote the free surface. Okay, free surface means that this is the surface of the liquid, and beyond which it is the atmosphere or a different kind of fluid. Okay, and in general, free surface would mean that it is exposed to the atmosphere. Okay, so if we consider this scenario, then say this is direction of this points towards the direction of positive z, then the gravity would act along the negative z direction. Okay, so that's why it is denoted as the negative z direction. So the equation of motion along the z direction would be minus dou P by dou z plus rho bz equal to 0, because the force because the fluid is not in motion, it is a static state, so the acceleration would be 0, so it is again 0. Then the body force per unit mass would be minus g, that is the gravitational along the force due to gravity. Then we can write we can simplify this expression as let me write it as, say, minus dou P by dou z minus rho g is equal to 0. Okay, now along the x direction, and say again also along the y direction, dou P by dou x and also say dou P by dou y would be equal to 0. So it would basically imply that P is not a function of x or y. Okay, then it will imply that P is only a function of z. Okay, so if that's the scenario, then we can write this partial derivative as a complete derivative. Okay, I hope this concept is understood, like when we can change the derivatives from partial derivatives to complete derivatives or ordinary derivatives. Okay, so we can write it as minus dp by dz. Now it is d, not dou. Okay, it's dp by dz minus rho g is equal to 0. Okay, so again, just we are using this expression here, so we can write minus dp by dz is equal to rho g, or dp is equal to minus rho g dz. Then if we integrate it accordingly, say pressure from point A to B, say if you want to find the difference of pressure from point A to B, then we have to integrate this expression from 0 to minus h. Okay, so 0 is the, say, the depth at point A, and minus h, because it's in the negative z direction, is the depth at point B. Then PV minus PA would be minus 0, integration of 0 to minus h rho g into dz. Okay, and if this rho g, this product of density and gravitational acceleration, is a constant, then we can take this out of this integration. So we can write PV minus PA as rho gh, or PB as PA plus rho gh. Okay, so this is again a very important expression to know. So let me just mark it as in a red box so that you know it's important. Then with this idea in mind, there was a elaborate discussion about the concept of gauge pressure, absolute pressure, and atmospheric pressure. So P gauge, or the gauge pressure, is basically the difference between the absolute pressure and the atmospheric pressure. So sometimes, like if you're mentioning that the pressure within a tire tube is say I'm just giving an example, say 5 kilopascal. Okay, so it will mean that it is 5 kilopascal. If it in the gauge pressure scale, it will mean that it is 5 kilopascal greater than the atmospheric pressure. Okay, so say if P, just give me an example, if P gauge is 5 kPa, then P absolute, like in terms of, if you consider in the absolute scale, it would be P gauge or gauge, whatever you want to say, it's fine, plus P ATM. So it would be, say, 5 kPa plus 100 kPa, just as an approximation. So atmospheric, so the total absolute pressure in the tube would be 105 kPa. So this is the absolute pressure. Okay, so this is the concept of gauge pressure and absolute pressure and atmospheric pressure. So this is the relation. Just like I've just taken this part in this side, so it becomes P ABS is equal to P gauge plus P atmospheric. Okay, so with these concepts in mind, then we look into two different pressure measuring devices. First is the barometer, and then second is the manometer. So again, say if this is the configuration for barometer. Again, like if this is the liquid level that is risen because of the pressure, again we can ask, there can be a concept of capillary rise. Okay, we can confuse with that, but there are scenarios where, since the diameter of this tube is much larger for the capillary rise to be substantial, then we can disregard the deflection in this value of h due to capillary rise. Okay, again, there have been discussion in the lecture. So keeping that idea in mind, so this rise of liquid will be primarily because of this pressure that is exerted on the liquid surface, and this would be a measure of this pressure in this liquid surface. Okay, so P would actually be, if we write it in another way, so P, this pressure P would be equal to PV, that is the vapor pressure because of this liquid in the tube. I will come back to vapor pressure part eventually. This pressure within this region, that is PV in this region, plus the pressure due to this liquid column. Okay, and that is found out from the expression of rho gh, right? So it will be PV plus rho gh, or something like P minus PV is equal to rho gh, that is written here. Okay, So this vapor pressure, as it suggests, it's the pressure because of the vapor of the particular liquid. Okay, for example, if there's, oh, okay, I have to charge my pencil for a while, but let us just consider. Okay, so if the liquid, I hope you are able to understand the diagram, then I'm just not pointing it out because my pencil is out of charge. So if I say that this liquid column is of water, okay, then because of the fact that at even at say room temperature, the liquid molecules on the surface of this water column would try to vaporize. Okay, would try to vaporize, and because of the fact that these additional liquid molecules are being imparted out of the surface towards this closed container, the pressure within that region would rise because of the evaporation of these liquid columns from the surface. Sorry, liquid molecules from the surface. Okay, and that's how the vapor pressure comes into picture. So if say there is a fluid, for example, there is a fluid, say alcohol, instead of water, instead of water, say if you're using alcohol, which has a higher tendency to evaporate at the room temperature, then the vapor pressure at this region because of the alcohol would be higher. Similarly, if you have another fluid such as mercury, which has a very less tendency to get evaporated because of the room temperature, then the vapor pressure because of mercury in this region would be again be very, very less. Okay, so sometimes because of this discrepancies in vapor pressure for different fluids, it's usually preferred that the fluid that has the lowest vapor pressure should be used in these kind of measurements. Okay, that's why mercury is usually used in these kinds of scenarios where the vapor pressure of the liquid also can aid to the accuracy of measurements. Okay, and that's why, since mercury has a very lower vapor pressure, that's why mercury is used in these kinds of barometric measurements. Okay, then finally there is a discussion about the measurements of pressure using manometer. Okay, again there were different kinds of manometers that were discussed. There is an inclined tube manometer. I will come into that. I will not go into the expression, but I will discuss briefly like why inclined tube manometer is used. Again, that was thoroughly discussed in the lecture, so I just skipped that part because just the concept of doing this pressure balance at at a particular with respect to a particular datum, that's important. So I will discuss that. These different classifications of manometers you can just discuss from your study from your end. Okay, I hope that's fine. So manometers are usually used to find the pressure difference between two different points in a duct or pipe. Okay, so for example, there is a fluid flow from A to B. Okay, from A to B, like basically the flow is in this direction. So you will eventually see that for a flow to occur from in this direction, that is from A to B, pressure at B has to be lower than pressure at A. Okay, so that's something that I mentioned here. So basically the flow occurs in the negative pressure gradient direction. Okay, so pressure has to be lower in the point where the pressure has to be lower in the point where the flow is moving towards. Okay, since the flow is moving towards B from A to B, then pressure at B has to be lower for this flow to occur. Okay, and you will see that accordingly we have denoted the liquid levels as well. Since the pressure at point B is lower, so the displacement of the fluid because of the pressures is lower at point A than point B. Okay, if you have any doubt, you can stop me and ask. Okay, regarding this manometer portion. Okay, so that's why you see, since pressure at point B is higher, that's why it is a higher tendency to push this liquid in this manometer. Okay, so if the pressure at point B was higher, then the liquid levels at this would be lower and liquid level at this point would be higher. Okay, so that's how this deflection, that's how we measure the pressure differences. Okay, so since pressure at point B is lower than pressure at point A, then this deflection of liquid would be higher in this region. Okay, then if we consider the datum is basically a reference surface from which we consider our measurements. Okay, so datum in this case I am choosing to be surface at the level, liquid level at the column A. Okay, within this point A. So let us name these points as C and D. Okay, C and D. Then I'm denoting this line as reference point as CD. Okay, so I'm using the red dotted line. Then the difference of liquid heights in these two regions is delta H. Okay, and the interface at point A is at height Z2 from point B and at a point of Z1 from point A. Okay, and these 2 points A and B are at the same level. Okay, since it's say in a simplified case, it's a horizontal pipe, so these 2 points are at same levels. Okay, now pressure at point C and point D are equal because they are at the same height. Okay, they are at the same height, so pressure at point C and point D would be equal. That's the concept of hydrostatics. So with that idea in mind, we now try to do the pressure balance at these 2 points. So pressure at point C is contributed because of pressure at point A, that is PA, plus the height of this liquid column Z1. Okay, so say if the fluid is say water in this case, say if the fluid okay, it's mentioned it's water, that's whose pressure we are going to measure, then the pressure because of this liquid column would be rho W into Z1 into G, okay, or rho GH, right? Then that will be equal to pressure at point D. So at point D it is contributed by this liquid column plus this liquid column, and these two liquids are different. So because of this, there will be PB, pressure at point B, plus Z2, that is the height of the liquid water at this region, into rho W, this is a density of water, into G, plus this height, that is delta H, or Z2 minus Z1, delta H times rho Hg, this is a mercury in this case, rho Hg times G, G. Okay, so is it clear till now, this expression how we have found out? Is it clear till now? Thumbs up or a yes in the chat box would be good. Okay, it's fine, like it's raised hand. Okay, Pradeep, you can ask your question. You can ask your question in the chat box. Kindly type your question in the chat box. Okay. Okay. So you can kindly write your question in the chat box. Okay, I'll look into it. But for now, let us complete this derivation. Okay, sorry that there's a mic issue in my system, so I'm not able to rectify it. That's why I'm requesting the students to write the question in the chat box. Sorry for that. Okay. Then PA minus PB. Okay, let us simplify it even further. I hope it is clear till now. Let's wait for Pradeep's doubt. Then if we take PB in this side and this Z1 the rho W into G in this side, then we'll get PA minus PB as rho W into G into Z2 minus Z1. That would be minus H, like Z2 minus Z1 will be minus delta H, plus rho Hg into delta H into G. Okay, so if we then take delta H S and G as common, then we can write PA minus PB as G into delta H into rho Hg minus rho W, or PA minus PB is equal to rho Hg, G into delta H into rho W, this is density of water. Just take this common, and this rho Hg minus divided by rho W minus 1. Okay, so actually this up to this part the simplification is not usually required. Like if you are able to find up to here, then also you can just find the pressure difference. It's that simple. But just to again understand it even a better way, Professor Chakraborty derived it up till this point. Then there is an important discussion, that is the error. Okay, so as Professor Chakraborty mentioned, that if this error in this pressure reading depends on this value delta H, okay, because rho Hg, rho W is again something that is constant, G is constant. The only thing that we are measuring is this term delta H. Okay, so if the error in reading of delta H is high, then the pressure reading will also be wrong. Okay, and if say the deflection itself is very small, okay, say if I go back here, if say the deflection itself is say in terms of millimeter, then how you can expect that we will be able to correctly find out this deflection. Okay, so there might be some deflection because of the capillary rise, right? There may be meniscus here, so instead of using say 0.01, you are measuring 0.012. So this will again lead to discrepancy in the pressure measurements. Okay, it's all about accurate measurements, but since if deflection is very, very small, then the error can also be huge. Okay, so if there's only a pressure difference of say 1 kilopascal, and if there's something that you need, then delta H will itself be very, very small. So the error can also be very, very high, because if delta H itself is very, very small, then there are higher chance of error in reading of delta H. So that's why there was the requirement of finding out the inclined tube manometer, where we find out the deflection in this liquid column is higher compared to these vertical columns, so that the error in the reading can be minimized. Okay, so I hope it's clear up to this. Pradeep, I hope okay, he's in the class, but you can just write your doubt in the chat box. I'll look into it. So meanwhile others, let us look into the problem solving part. So I hope it was clear till now. Again, the problem solving part is also not that extensive. We'll try to finish it as soon as possible. So I hope the screen is visible. The questions, I hope they are visible. Okay, thumbs up would be fine. Thumbs up, or yes, you can just. Okay. Okay, let us Akash. Sir, from this equation we get pressure difference if you have to find individual pressure at point. How? Oh yeah, again, thanks. That's what I wanted to discuss actually. That pressure, these manometers are usually used to find the pressure difference between these 2 points. Okay, and finding absolute pressure is actually a bit challenging task. Like if you are trying to find the pressure, and not challenging, I would say it cannot be found out from manometer. There are different devices for it. There is a device known as piezometer, for example, like something close to this barometer. Like if you're say trying to, let me just try to draw it. If you're trying to find the pressure say in a duct and try to use a tube to find the pressure at this point, say at this particular, so say this is the say pipe is in this direction, moving in this direction. Okay, and this is say the front view, and pipe goes along these directions. Okay, so I'll just label it. Yeah. So if you're trying to say if you're trying to find the pressure at a point say in this region of pipe, let me name it as point A. Okay, then what you can use a piezometer that again works on the same principle. There would be a liquid used here to find the deflection. So pressure, because of the pressure at point A, there will be a deflection in these liquid levels. Okay, so it will say rise up to a certain height, say delta H. Then depending on the type of fluid that you use, say rho F, then pressure at point A would be rho A, PA would be rho F into G into delta H. Okay, so there's something that can be done, okay, using piezometers. And if you would have attended say the fluid mechanics lab, then there is a very trademark experiment of venturimeter, where you say for, okay, again venturimeter is again a topic that we have not discussed till now, but since you have pointed it out, I'm just telling you. So there is a venturimeter, there is a special tube of this shape, like a fastly converging entrance part and a slowly diverging exit part, or the so here you see there are different tubes that are placed at different sections of the duct, okay, or the venturimeter. venturimeter, so you will see that the pressure levels at those particular points are also shown by the liquid levels here. So you will see that the liquid levels here are higher, here it is lower, then again it gradually increases. Okay, so if you draw some lines, you will be able to see the pressure variation along the length of this venturimeter. So these pressure tubes, or what they say, okay, just piezometer. These piezometers are actually used to find the pressure at these particular regions. Okay, so if you name it, say A, not confuse it, say A, B, C, D, E, sorry, E, F. So these pressure taps, pressure taps actually, these are pressure taps or piezometer in this case. So these pressure taps usually help us to find the pressure at these particular points. Okay, so that's how we can approximately find the pressure at these particular different sections of the pipe. But as you rightly pointed out, these manometers are usually used, at least in this case, is used to find the pressure difference at point A and B. Okay. Okay. Thank you, Akash. I wanted to point it out, but I thought like it's fine, but it's good that you are so interested. You're finding out what I am trying to hide from you. Fine. I'm not trying to hide. I'm just, for the scope of this course, I'm not discussing that elaborately. Okay. Okay then. So let us look into the question first. Now it's time for you to do some work, and I will see. So the first question is, I hope the screen is visible, and I think I should zoom out, zoom in a bit. So yeah, I hope the questions are visible. Okay, so consider a 0.15 millimeter diameter air bubble. Okay, it's air bubble in a liquid. If the surface tension in the air liquid interface is 0.040 Newton per meter, the pressure difference between the inside and outside the air bubble is 3.23 kilopascal. State true or false. So basically you need to find the excess pressure. In this case it will be 2 into sigma by r. Just do this calculation and tell whether it's true or false. Okay. Try it out. I hope the question is clear. Not that difficult. Everything is given. Just need to substitute the value. Say, I will just write it for simplicity. Excess pressure is given with delta P into 2 sigma by R. Everything is given. Just substitute the value and just tell whether the pressure that they have mentioned, whether it is correct or not. I will wait till say 7:13, 2 more minutes, and then you can see the answer. Quite simple. Just substitute the value in the calculator and just let me know. Okay. Okay then. It's fine. It's quite simple actually. So the key is in let me just, the key is in the question, that is air bubble. So actually there might be confusion within, like whether you should consider this into 2 or whether just this. So since it is uh, air, so air usually, like, it's difficult to form a hollow air bubble within the liquid. So can so that air bubble within the liquid would be like composed of air, like it would basically be a air droplet within within the liquid. Okay, so that's why when it pops out, the air comes out of that particular bubble. Okay, the air is trapped within that within this bubble. Okay, so it will be 2 into sigma bar. It's a solid bubble, not a hollow bubble. Okay, so we just need to substitute here. So if I go back in my notes, so just substitute the value. So delta P will be 2 sigma by R. So 2 into 0.04 by 1.5 minus 3. Let me just do it myself, calculate as myself as well, so that let me check whether it's correct or not. 0.15 into 10 to the minus 3. So it turns out to be okay. So let me just, yeah, yes, exactly. So it would be its diameter, right? So it would be divided by 2. That's why I was correct. Yeah, it's correct. Thanks, Ketan. It's false. Yeah. So it is coming out to be 1.066 into 1.1066.66 Newton per meter square, which is not what it is mentioned in the question. Sorry, not what mentioned in the question. So this is false. So let's look in the next question. Which of the following forces are applied to the considered to be which of the following forces are required to be considered while deriving the equilibrium height for a capillary dipped vertically in a liquid? Okay, so basically asking what are the things that are taken into consideration where while finding the expression for capillary rise. Okay, H. So viscous forces, gravity, surface tension forces, both B and C. So which will be the correct answer? Again, simple multiple choice type question. So can you tell? D. Both B and C. Akash says both B. Pradeep says D. So if like both B and C, yeah. So this is the correct thing. So both gravity and surface tension forces will come into picture. So if you look into it, so if I'm not wrong, it is 2 sigma cos theta by rho g r. Right. So surface tension forces are taken into account by this, and gravity is taken into consideration by G. So both B and C are relevant. Okay. So question number 3 is a soap film is trapped between a vertical frame and a wire. This is again an interesting question. So let us try to understand it first. A soap film is trapped within a vertical frame and a wire of length 1. Okay, so this is the film. Say it's a soap film, and this is the wire. Okay, like basically, like if you dip this frame in a soap mixture and then try to extend it, you will see there is a soap bubble here. Okay, or soap film here. Like basically you see, right, like if you dip this kind of loops in the soap mixture, then if you blow air within this hollow loop, then you will see bubbles coming out, right? So same concept, just dip this frame in the liquid liquid soap mixture, then you will see that there is a liquid film in this region, and this frame is extended downwards by the mass that is attached to this wire. Okay, like once the mass is attached, so this wire will come down and there is a soap film in this region. Okay, I hope the description is clear. and the length of this wire is 1 centimeter. Okay, this is length of this wire is 1 centimeter. If the surface tension is given as 0.072 Newton meter, that is sigma, what will be the value of m in kg such that the wire remains in equilibrium? Okay, so what should be the value of this m so that there is an equilibrium between the surface tension forces that tend to pull this in this direction and the mass that tries to pull it in the downward direction. Okay, so basically a balance between these two forces. So what would be the value of that mass m? So I not say it's that difficult, but it's a bit conceptually heavy question. So you need to understand which are the surfaces that are behind balancing the mass m. Then you need to find the surface tension forces, find the balance between the surface tension forces and the mass, and then tell me the value of m. Okay, I'll say I will wait till 7:22 and then you can tell me the answer. Okay. So 2 more minutes, then we can look into the answer and then proceed to the next question. So like, okay, fine. So the key thing is to understand the length of contact of the soap bubble or the film with water. So if you know that C, okay, Akash says option C, very nice. Others, what are your opinions, answers like which can be correct? Okay, so as I was mentioning, okay, you can continue to calculate. I will just try to say it might help others as well. So say the thing is, the liquid that is into consideration is soap. So we usually know that soap, when it forms a bubble or interface, is usually a two surfaced interface, basically a hollow surface, right? So in this case, when the wire is like in contact with the soap, so we can consider that there will be two films, one in the either edges or surfaces of the wire. Okay, so let me try to help you visualize it. So if you are taking a very zoomed in version of this pipe, okay, so sorry, not pipe, wire. So it's something like, if I look into this side view, if I try to view it from this part, so I see something like this is the diameter of, this is the surface of the pipe, sorry, wire. Then let us do, this is the wire, very zoomed in version. And then the soap film will be something like, one soap film will be attached in this edge, and other soap film will be attached in this edge, and basically this part will be hollow. Okay, that's the characteristic of soap bubble. Okay, and that's where the special case comes into picture, because of soap bubbles, or the expression for excess pressure. Then there would be excess forces, then there will be sufficient forces because of this film as well as this film, and the mass m is acting along this direction, m, right? Of course, it is in the center. I'm just showing you the direction of forces. Okay, so then there are two liquid films or in surfaces that are in contact with the wire, that is trying to pull this mass in the opposite direction. So the force balance would be 2 times sigma into L, right? Force would be basically be the surface energy force coefficient times L, because surface energy coefficient itself is force per unit length, right? 2 into sigma into L would be equal to the mass times the gravitational acceleration, or mass m would be 2 sigma L by g. Okay, so that's the key or crucial element of this question, to find this factor 2. Okay, so once you substitute the value of sigma, L and g in this expression, you will find that the value of m is 0.000001467 kg. Okay, so let's look into the next question. I hope this was clear. Okay, so let's look into the next question. For liquid molecules on the interface of a liquid in an open container, forces exerted by the other side of liquid molecules is same as the exerted by the gas molecules above the interface. Is it true or false? It's something that we started the class with, like the very beginning of the class I discussed this part. So is it true or false? Are the forces in the liquid side and in the vapor side the same in the interface on a liquid molecule? Very simple, please. The cohesive forces and adhesive forces, how surface tension comes into picture? False. Yeah, thanks. It's not, because the liquid force along the liquid in the liquid part would be higher than the force because of the gas molecules on the liquid surface. That's why there will be discrepancy of forces, and because of this discrepancy of forces, the surface energy or the concept of surface tension comes into picture. So it is false. Again, it's a very simple question, just the substitution of values. A capillary tube of 2.4 mm diameter is immersed vertically in water exposed to the atmosphere. Determine how high the water will rise in the tube. Okay, basically you're asked to find the capillary rise. Take the contact angle in the inner wall of the tube to be 0 degree. Okay, and the surface tension to be 1 Newton per meter. Okay, just substitute the value of 2 sigma cos theta by rho g r. Okay, so every parameter value is already given. Just substitute the value of this here and then tell me the answer. And the options are also given. Then you can just tell me. Simple substitution. Thanks Sanu. Thanks Pradeep. We're correct. So let us look in the next question. Substitute the value of these parameters in this equation. It's just simple substitution of values. Then tell me the value of capillary rise. Okay. Again, since the contact angle is in in the acute category, like it's less than 90 degrees, so you can use the same. Yes. So Akash says the answer is 0.169. So others, did you find anything else? Any other answer other than 0.169? I'm sorry. Okay. So uh, so the answer is indeed 0.169 meter. I'll just look into it. Like if I just substitute the value of theta is 0 degree, sigma is 1, and rho is 1000 because it's water, and G is 9.81, and R is 0.0012, then I get H as 0.169 meter. Okay, that's quite simple. So I hope it's clear. Others, like if you have any doubt, you can just ask, but I think it's just simple substitution of values. Okay. So let us look at the next question. Again, a statement type question, statement assertion type question. A capillary tube is inserted in water kept in open container. Okay. Open container and capillary tube. So it is related to capillary rise. Water level inside the tube shall rise above the level of water level outside. Okay. Water level inside the tube shall rise above the water level outside. Okay. Basically, like if you insert the capillary tube here, they are saying that the water inside the tube is in water, so water level here should rise up. The first statement. Second is, the cohesive forces between the molecules of water is greater than the adhesive forces between the water and glass. So that's the assertion. It's because of this that this rise is happening. So is it true or false? Or like, I'm not saying true or false. Which of the options are correct? Yeah. Cohesive greater than adhesive. So is this the case? In the case of water? So Ketan, Akash, Sanu, all are saying C. So it is indeed correct. So as we saw that in the case of water, the meniscus that is formed is a concave shaped meniscus. So the adhesive forces between these liquid molecules and the solid surface of the capillary tube is higher than the cohesive forces between these liquid molecules at the interface, and that's why we see this kind of meniscus to be formed. Okay, so that's why there is a capillary rise in the case of water, but in the case of mercury the case is just opposite. The cohesive forces between the mercury molecules are higher than the adhesive forces between the mercury molecules and the the inner surface of the capillary tube. That's why the liquid level or the mercury level in that particular case in the capillary tube falls down. So it will basically be something like this is the mercury surface, then this is the capillary tube within the mercury, then the mercury level would indeed go down and a meniscus form would be of a concave shape. Okay, concave shaped. I hope. Okay, I think so. Answer is correct. So A is true. Water level will rise, but it's not because of this fact. Okay, so cohesive forces of the molecules of water is lesser than the adhesive forces between water and glass. Okay. Thank you, Pradeep, Ketan, Sanu, and Akash. Let's look in the next question. Okay, so this is again the question based on manometer. So this is what they have discussed thoroughly. We took an example and discussed it thoroughly. So let us look into it. Okay. A manometer is used to measure the pressure inside the gas tank. Okay, and their key terms is gas, pressure of a gas in a tank. Okay. The fluid used has a specific gravity of 0.97. So, okay. And the manometer column height is 45 centimeters. So this is 45 centimeters, and datum you can take it at this surface. Okay. If the local atmospheric pressure is 97 kilopascal, so the pressure here is 97 kilopascal. Determine the absolute pressure within the tank. Okay. So here I think the only new term is the specific gravity. So the specific gravity of the fluid they have mentioned, okay, fluid. So in this case, it would be the ratio of the specific gravity of this fluid, say rho fluid divided by rho water. Okay, so this would be specific gravity. So rho fluid of this particular fluid, say if it is rho f, then rho f would be specific gravity times the density of water, and it's quite well known. So let me leave it as an exercise for you. Rho w is something that you should know. So with that idea in mind, can you tell me the capillary rise? Sorry, so not capillary rise, I'm sorry. Can you tell me the pressure in this particular region, P? Okay. So I will give you 4 minutes for this question. Simple substitution of values in the expression. P is equal to PB is equal to PA plus rho GH. And the key thing is to understand the density variations between a gas and a liquid. Okay, so there is a certain approximation that you have to take. Oh, I'm sorry, the screen might have gone out. Sorry for this. I'll share my screen again. Sorry for this issue. Share screen. Okay, continue. Okay, so I hope the screen is visible. Screen is back on. So sorry. Okay, yeah, so as I was mentioning, there is a concept of this density variation between liquids and gases. So there is an approximation that you have to take here to consider the fact that in some scenarios, if some parameters are absent, we can disregard the pressure because of the gas column, because of the very fact that the gas has a much lesser density than water. Okay, quite reasonable approximation. So with that idea in mind, with this hint, can you tell me what would be the pressure at point P? Absolute pressure, actually, absolute pressure. Okay, 100.6. Oh, I'm sorry, the screen again has gone out. Sorry for this issue. Okay, forgive me. Others can try. Okay, Akash says 100.6. Others, can you please try as well and let me know. Let me also try from my end and try to evaluate. So okay. Pradeep says 101.28. Others, can you try? Pradeep and Akash says it's Pradeep says it's D, Akash says it's A. So both of you, okay, let me give a hint. One of you is correct. Now you can just see which is correct. Okay, others also got some hint that one of them are correct. So which is correct, you have to. Ketan also says D. So Akash, it seems like more people are opting towards D. So can you reevaluate your calculations? I'm not saying you're wrong, but okay, yeah, just try once whether it's making sense or not, then we can just see. Okay, so it seems like Akash, Pradeep and I'm sorry, screen is just okay. As I mentioned, it seems that Akash, Pradeep and Ketan, if I'm not wrong, he has found the answer. So seems like they have understood like the approximation that I was mentioning. Okay, so let me just now discuss about it. So the approximation is that, so you might see that the height of the gas column, like if I go in this diagram, sorry, the specific height of this gas column is not mentioned. Okay, it's not mentioned here. So you might initially think that, so if we do pressure balance, say if it was say Z1, I'm just saying in case, so pressure balance as we have discussed for manometer, it was something like P, it's P plus this rho G Z1 would be equal to rho F, it's also F, no, it's rho F plus rho F into H into G plus PATM. Okay, so if this was say mercury instead of gas in this case, then this pressure because of this particular liquid column would have been substantial. Okay, but since this is gas, then compared to this deflection of height this liquid column or gas column is much lower, then we can just, for the sake of lack of information, particularly in this question, and it's a good approximation if we disregard this portion as well, then we can disregard the contribution of pressure because of this portion, then P would just be P, if we disregard this, it will just be P equal to rho F G into H plus PATM. So once you substitute it, you'll get that P is equal to PATM plus rho GH, that is this. Then PATM is 97 kilopascal or 97,000 Pascal plus 1000 into 0.97 into 981 G into HO, sorry. Oh yes, 1000 into 0.97, that is the density of the fluid, into G, that is 9.81, and H is 0.45, that's 45 centimeters. So once you do that, you will find that P is 101,282 Pascal or 101.282 kilopascal. So the correct answer in this case would be option D. Okay, so option D is correct. Akash, you can just verify your calculation. I think it's just there might be some mistake, but it's fine. Okay, so the next question is, which of the following are correct regarding obtaining a proper reading using a barometer? Okay, so the options are: the vapor pressure correction for the barometric liquid is usually neglected in the case of mercury, as its vapor pressure is usually quite small over different temperature ranges. Second is, surface tension effects are assumed to be negligible unless the tube diameter is extremely small. C, local curvature of the interface are not considered if the surface tension effects are small. And D, compared to mercury, other less dense barometric fluids will lead to lesser liquid rise for the same pressure difference. Okay, so I think at this point of time it's just understanding which of the statements are correct, not only regarding barometer, but just understanding which are correct or wrong. Okay, so I think I have discussed all the concepts. Akash says A. So which of the following is mentioned? So are B, C, D, like none of them are correct? Can you say, look into it? Okay, let me give a hint. A is absolutely correct. I have discussed about vapor pressure because of mercury. That's correct. But all, Saurabh says all. So what about others? So let us see all. Let us look into D. Compared to mercury, other less dense barometric liquids will lead to lesser liquid rise for the same pressure difference. Okay, so we have P. Let me just write it as P S rho GH. Okay, or let me write it as P is equal to rho 1 G H1 and P is rho 2 G into H2. Okay, we are measuring pressure with different kind of fluids, and this will it will result in different liquid rise in the barometer. Then say if rho 1 is less than rho 2. Okay, if we equate these things, that is, since pressure is same, so rho 1 GH1 is equal to rho 2 GH2. If we consider disregard G, then rho 1 by rho 2 is equal to H2 by H1. So if rho 1 is less than rho 2, this would basically imply H2 is less than H1. Okay, so if the density of fluid is less, then the deflection in the barometer, that is H, would be higher compared to higher dense fluids, like for example mercury. So they are mentioning this less dense barometric liquids. Okay, so option D is incorrect, so all cannot be true. What are the other cases? A is also correct as I mentioned. Are B and C correct? So surface tension, as I mentioned, for let's just say capillary rise, like if H is very large, would you observe capillary rise? Okay, so okay, just to save time, thanks for trying out. Like the correct answer would be A, B and C. Okay, so D is incorrect as I have shown here. D is incorrect. So A is correct, as I mentioned, that vapor pressure because of mercury is lower because it does not tend to evaporate quickly. Okay, so vapor pressure because of mercury would be lower. Then surface tension is assumed to be negligible in the case of if negligible unless the tube diameter is extremely small. So if the tube diameter is very less, then only the surface tension effects or the capillary rise would be considerable to create deflection in the liquid level rise in the barometer. Okay, so if the diameter of the tube is considerably larger than for the capillary effect to show up, then this surface tension effects is not that in the measurement of this value of H in the barometers is not that considerable. Okay, and finally the local curvature effects are not considered if the surface tension effects are small. Again, these two are interrelated. So if surface tension effects are not that considerable, then we can disregard this local curvature of the interface. Okay, so I hope it's clear. So final question is piezometric. Again, it's a conceptual question, it's true or false type. Piezoelectric pressure sensors are made up of materials which, when subjected to a pressure difference, converts it to an output optical color signal, can be calibrated against pressure levels. So I think the key is in this term itself, piezoelectric. Okay, so if the input is pressure, what kind of output does a piezoelectric device would generate? Would it be an optical output or different kind of output? And just try out, just in the term itself, piezoelectric devices. Like if there's a mechanical input. Okay, so Saurabh says it's false. So others, can you throw some light into it? Okay, Shanavas say electrical signal output. Yeah, yes, exactly. That's correct. So you're right. So piezoelectric devices, as the name suggests, would convert mechanical inputs, that is in this case the pressure. Again, I'm sorry, the screen got disconnected. So this is pressure in this case into an electrical output, which then can be used to calibrate the systems to read this pressure accordingly. Okay, so that's why the this would be false. The optical, it would not generate any optical output, but rather generate electrical outputs that can be used to calibrate and consider the pressure measurements. Okay, so that's all for from my end for today. Sorry. So I hope it's clear. So if there's no doubt, then we all can meet in next week discussion. Okay. Here in static liquid remains constant at all, increases linearly, decreases linearly, remains constant. Static liquid remains constant at all points and increases linearly with depth. It's something for you to find out. So the key would be, I guess, this equation. I can give you a hint. So if we go in depth, what do you think the pressure levels would be? So that's what you can think of. Okay. So okay then, thank you everyone for attending this week's discussion. Let us all meet in the next week. Okay. Thank you then. Yeah. Thank you, Akash. Thank you, Pradeep. Thank you, Sanu. Thank you, Ketan.